Database logs are a critical component of any DBMS system in order to ensure durability and crash recovery, if you will. So logs like, I'm referring to logs such as the write ahead log, or WAL for short, WAL that is, the redo logs, and the undo logs. These are the only three that I know. There might be other type of logs that are there for specific implementation, but I think these are the three most popular. In fact, you can argue that the WAL is actually identical to the redo logs. And I'm going to talk about all of this in this episode of the Backend Engineering Show. It's been a while, and I'm almost recovered now, so I can do videos like this. Yay, nice. Coffee time. Speaking of coffee, I partnered with a company called Committeer. They do fantastic coffee. When you brew coffee, there are so many things that you need to do to nail the quantity of the beans first, to grind them in a specific size, how coarse, how fine the beans need to be grinded. And once you grind it, then you brew them by basically pouring water into them, right? And the temperature of water really affect the taste of the final product, which is the coffee. You can get into warm coffee. If you put too cold of a coffee, then you get basically water flavored coffee, if you will, or coffee flavored water. If you put too hot, then you feel the burn, and that's what you basically taste in diners coffees. It's like always like burned, and some people enjoy the burned flavor. That's why we have dark roast, and this is like a side of me that I don't talk about in this YouTube channel. I usually talk about it on Instagram. But Committeer, what they do is they nail all these parameters in a perfect manner, and then brew the coffee for you, and then they flash freeze it at that moment of time, and they send you these nice capsules. So what you do is you take these capsules and you just take it out, put it in a glass of water, pour hot water, and that's it. You enjoy that cup of coffee. And this is actually Committeer. This is if I'm not mistaken, this is Onyx coffee, so it's a medium roast, but it's fantastic. So I'll leave a link below if you're interested. Go to committeer.com/Hussein Nasser for $20 off your first order. And thank you for Committeer. Welcome to the Backend Engineering Show with your host, Hussein Nasser. And if we really think about durability in database system, you really need to think about how do you persist data, right? Well, you might say, okay, you have tables, you have data structures on those tables, such as indexes, sequences, constraints, stuff like that. And these live in files because that's what we have today, file system. So we have to work with files. You might argue with that. No, we can work with block storage directly, but most generic implementations work with files, and there are pros and cons, right, to that. Right? And I like to always think about this, Think about there is not only one way to do thing, and never pigeonhole your thing into one thing. Always look outside the box, as cheesy as it may sound. Trying to look outside the box and then understand why do you say the things you say, So things live in files, and we're working with data files. So table live in a data file, indexes live in a data file, and this is up to you as the database implementer to whether to put these two into one file or put them in separate files. There are pros and cons for both cases, right? And whether you put all indexes in one file or put each index in one file in its own file, it's all really depends on the implementation. And this is something we never think about as backend engineers, like, because hey, it's behind black box and the database does this thing. But it's good to understand how database is implemented, because the database is just a program at the end of the day, right? It's not really, well, what I was about to say rocket science, but you can argue it is as complex as rocket science. Database engineering. So when I make a change as a transaction, I begin my transaction, I start changing my table. The changes that I make to my table will trigger side behavior to update indexes. And these indexes need to be updated as a result. And the tables need to be updated as a result. The tables consist of pages, and the pages are touched and getting dirty. And at the end of the day, we gonna say, commit my changes. I just made a bunch of changes. Go ahead and commit them. Now, if I say commit my changes, what does that mean? It means logically, I want anything. That's high level speak. Everything that I wrote, I want it to be there forever. I want to see it next time I read, right? And this means I want it to be durable. That means if the database shut down after I successfully committed, and that's another thing. What does it mean to successfully commit? It means I receive a successful synchronous response from my commit operation. So I say, yup, all done. When you tell me, yup, all done, I assume that even if I shut you down in that second, if I unplug you, I come back, everything that I wrote should be there. So if we go back to this commit operation for a minute and ask yourself, how is this actually implemented? How can I implement it? Let's not get pigeonholed again with implementation. One way you would implement it is say, okay, anytime I write, if I begin my transaction, I start updating a row and inserting a new row, and I doing all these changes and I update the indexes, I am going to make all these changes in memory. Because you see, if I want to update row number 7, I need to fetch the page where row number 7 lives and update the page in memory. That's what I'm going to do. That's one implementation. I'm going to write in memory. Then I'm going to insert a new row on the same page in memory. And then I'm going to insert another row, but this table is clustered, so the page is at the end, at the tail of the table. So I need to fetch that page, fetch it, put in the pool, the buffer pool, the memory, and then write to it. And I keep writing to memory, writing to memory, writing to memory. And that's fine, because these changes are dirty and I didn't commit, right? Now, if the client tells me to commit, I'll take everything that I have in memory and I literally just flush it to disk. That means I am overwriting the same location where the page existed in the file with my changes. And you can see if you make a lot of changes, the commit operation will be slow, right? This implementation. Naturally, because all of this stuff is your memory and you have to take time to persist these changing to disk. As you write them to disk, you're taking a hit. You're going to the disk and writing these different pages, and that might take a while to write all this. And the problem here is not the time per se. of this implementation. The problem here, what happened if you wrote half of these pages and the database crash in the middle of your commit? That is dangerous. Why? Because you just flushed something and you changed the presentation of the table for a transaction that was half-assed. It was half committed. And what does it mean to half commit? Well, it doesn't mean anything. A half committed transaction is a rolled back transaction, is a bad transaction and should not be considered. That's rule number one in ACID transactions, atomicity, right? So that's a problem. That implementation sucks, right? But it was so good because my writes were so fast, right? Because I am writing, all my changes are in memory. But that sucks. So what people did, what computer scientists did, we said, okay, computer scientists said this. What if, as I am writing these dirty changes, I keep a log, an actual journal of what exactly changed, not the whole thing. Because remember, when you pull a page of 6 kilobyte, 8 kilobyte page, depending on the SSD size and the database page size and how they agree on that, and you change 1 byte, or you change 32 bits, or whatever the size of the row you change, and you said flush, there is no flush 1 byte when it comes to disk. Not until we get byte addressability on SSDs and hard drives. It doesn't exist. Today, the minimum size is called, and people argue about this, it's called a page, I believe, in SSD. Sometimes it's called a block. Sometimes it's called erasable unit. In a database, in hard disk, it's called sector. There is a specific size, and we don't care what it's called because names don't go anywhere, to be honest. I've been in this business for a long time, and everybody invents a name from their ass. Okay, so you can invent your own name from your own ass and be satisfied with that. But what the technology does not allow us to write 1 byte because of physical limitation of the disk. Okay, because it's not worth it to write 1 byte. I believe that's the reason. So we write a bunch of them. So if I change something, that I have to write 8K. Even if I change one thing, right? And that's costly. So that back to what computer scientists say, okay, because we have this limitation, and instead of I changed one thing, let's keep a log of that thing that changed. That's a good idea. And let's make sure that that log is immediately persisted to disk, because that log, that journal is the source of truth. You change this. Row A became B, and column 7 in row 6 became this value, and the string hello becomes word. You make changes. You just journal the changes, and this is called the write ahead log. And it's called write ahead because you're writing ahead of time, almost like you're predicting what's gonna change, because that's what's gonna change. So if I write this now and I have this log and I make sure every write I do to the WAL, to the write ahead log, is persisted to disk, then that's nice, because I can keep my dirty pages in memory. And now, if I say commit, I already written all the changes to the log. I have a journal of every possible thing that my transaction did, and all other transactions as well. So I can replay this if I want to. So now let's take this into consideration again. You have a presentation of what the page looks like or the table looks like on disk. You pulled it into memory and you start making the changes in memory. You still make the changes to that page in memory, but you also take note of what these tiny changes, just what changed into this wall. So the wall will be so compact and it's also compressed and it's done all sorts of stuff to it. And you flush the changes to disk. You keep those in memory. You might say, hey, what, you're not flushing this? It's okay not to flush it. We're going to talk about it. We're going to need to flush it eventually, but not immediately because these are expensive. These are large pages. So now you keep all these changes. And now you say commit. Commit the transaction. What is the minimum amount of work that the database needs to do to commit? Well, all we have to do is just commit, make sure all the WALs committed. And if the WALs committed, we can persist the fact that this transaction is successfully committed. And we can crash if we want. You might say, Hussein, the pages are old. That's true. The pages in the disk still is in its original representation, but the memory was the final one. It was everything we made the changes, it was in the memory. We don't have to commit that. We can try later, but we don't have to. So let's take this consideration that I committed all the changes in the wall or the write ahead log, and boom, my database crashed, but I committed. It comes back up. It detected that, well, the page now is completely out of sync with the wall, right? Because the wall is ahead in this case. The write ahead log is literally ahead of the data files. The data files was the old original one. So the database knows this. How does it know? Because there are records of this. And it says, oh, wait a minute. It starts up and says, oh, wait a minute. This is old. I can't let people read this because nobody reads from the wall. That's another question I got from the database course. What if can I read from the wall? Can my transaction go to the wall and read it? That's a bad idea. Well, you can. Let's not say anything is a bad idea. It's just, you can. If you can do anything you want. You own the software. If you're building it, you own the software. You can write anything you do. You own it. You can decide, hey, let's read from the wall, the changes. But the work that you have to do is enormous. And clients don't necessarily want to do that. They want to read a nice tucked in page and they want to just crack the rows and read them. They don't want to just figure things out. Because remember, this only has the changes. You still need more stuff. So you'll end up reading multiple places. So it can be done, but it's hard. So the database crashed and stored back, and then it detected that there was a crash. And the page that is on this is out of sync. The wall is ahead of us, right? The write ahead log is way ahead of us. So the wall is ahead. So what does the database do? Takes that page and then reads it into memory and says, wait a minute. Let me apply the changes in the wall to this page, and then starts redoing the changes, because at one point we did that changes. This is a redo of these changes. So you start redo these changes, applying these changes again, because this is have been done at one point, right? But we lost it. Now we're redoing it. That's why the wall is also called the redo log. So we're redoing these changes. So take that beautiful old stale page, which is consistent, by the way, because at that moment of time, we didn't then apply all the changes that that transaction or other transaction made until we are done with the wall. And now that page is freshly dirty with the latest changes. So I can have clients read from this dirty page. And I can safely flush this page to disk, right? And now, when you flush this page to disk, you're now consistent with the WAL effectively. You might say, now this is a very good point, right? We talked about the data files and the indexes, and we talked about the WAL. And how often should I flush data files to disk? It's all of this is configurable for you as a DBA. There is something called the WAL size, how big the WAL can get. The WAL shouldn't go infinity, right? Because once I flush that dirty changes, the WAL can be purged, right? Because those changes are already synced with the data files. There is no point for me to keep these old WALs, all changes, because those changes has been completely, the only purpose of the WAL was in case of a crash, I can recover and redo the changes. And if you did them and all the data files are in sync, why the heck do you keep them around? It's just wasted space. That's why the WAL is also presented sometimes as a circle. Right? You write, changes. And once you end the end of the circle, that means it's time to flush. The WAL is almost full. Go and flush every data file, data page in memory down to disk. And if the flushing was successful, go and purge the WAL. You might say, Hussein, isn't this the same problem that you originally started when you started this show? You talked about that what happened if while you're flushing the page, the database crashed. That's fine, because we know, right? We know the moment where the pages were consistent, and we know that the WAL is not, whatever's in the WAL is the truth. So you go back and you say, okay, from this point, that's when things were good. That changes is all garbage. So you need to remove all these changes, and then you have to reapply them again. So that's another thing that the database do. So in the case of a crash, so it's a complicated process, right? So they take care of all of these situations. So that process that we talked about just now, where the flushing of these dirty pages so that we can get rid of the WAL, is called checkpointing. And it really happens at the most random time, because checkpointing, if you think about it, is a data intensive, IO intensive operation. Because now, while I'm doing checkpointing, it depends really on the database implementation, but I believe things need to get paused during checkpointing, because you really need to make sure that no new things comes to the WAL as you checkpoint. You can argue that, hey, I'm gonna put a checkpoint point on my WAL. This is where I'm checkpointing right now. Write everything, flush everything to disk, and then the WAL can continue to grow, and transaction can keep coming in, and you can implement something like that, right, with a little bit of finesse engineering, I guess, right? But I believe it's gonna be a little bit complex. But these checkpointing operation, and Postgres warns about it, MySQL warns about it, every database warns about it. It's like, hey, just watch out for this, because CPU, RAM, disk activity will spike as checkpoint happens. And this can happen at the most random places. You might have a very high intensive workload, right, that is happening at the same time as a checkpoint, and that will suffer as a result. Do you want to suffer? Well, life is suffering, unfortunately, so we all need to suffer. So sometimes we cannot escape this stuff. But you can understand now that if this happens, right, this explains why sometimes a query takes fraction of a millisecond, sometimes it takes 50 milliseconds out of nowhere. Like, what is this? Because the database might be doing something. So what do? Well, you try to make the wall as short as possible, right? As small as possible. If you make a wall small as possible, then the checkpoint size will be smaller, so the flushing will be more frequent. The checkpointing will be more frequent. And in this case, you're only flushing certain amount of data as a given time. And that could be tolerable, and it will be almost consistent. And you can argue, yeah, let's make the wall so large such that, yeah, I don't want to deal with checkpointing until, I don't know, certain time, right? But if you keep that for a long time, then it can also grow into other problems. Everything is a trade-off, unfortunately. I don't have solutions to any of this stuff. It's just understanding that this exists and we have to deal with it. All for what? For durability. We are doing all of this for durability. We want to be durable and we want to recover and be consistent in case of a crash. If you can guarantee that you'll never crash, remove the wall. I dare you. Remove the wall. So some say computer scientists built a wall and the DBAs paid for it. Get it? No? That was a bad joke. All right. So we talked about redo logs, which is the wall, the write ahead log. Okay. And go to their configuration and you're going to see this plastered everywhere. Wall this, wall that, wall time, wall this, wall flush time. Well, do you want fsync or not, right? Yeah, let's talk about this actually, the fsync in the wall. So you see, if you are building your database on top of an operating system, you might say, what kind of stupid statement is that, Hussein? What else are you going to build your database on? Hey, I have to be very specific because you might build your own operating system that is a database. Yeah, because you might build your own OS that happens to be a database without the bloat of the operating system. But if you decide, like any database that is, to build your database that lives on top of this bloat that is called the OS, the general purpose, right, OS, then you have to live with the rules of the OS, which is Linux or Windows or Mac or Temple OS. Is that an OS? Then there is something that the operating system does. Because it's general purpose, it doesn't trust any app. It says, hey, all apps are stupid. So the apps tend to do some repetitive job. They write to the same file multiple times in the same microsecond. You know, if the operating system let that writes go to disk immediately, your SSD will be dead effectively, right? In few years, let's say, right? Right, because like, how many times do you write save, Control S, Control S, Control S? Imagine all these writes going immediately to this, right? No. What the operating system has is like, it has a file system cache. So if you write something, it says, do you really want to write it? Let's just wait. Let's buffer these writes. So it buffers these writes in memory, and it keeps them in memory, in the cache, hoping that the same page will receive more writes because same problem, right? Because if I write 1 byte, I have to flush the whole disk. It's just not worth it. Not disk, whole page, right? It's just not worth it. So let's just wait for more writes that hopefully this dirty page receives, so I can flush the whole page with rich, dirty writes. The more writes the page receives in memory, like the better the economics of writing a page. Because otherwise, if you change one character and that writes to disk, and then you change another character and that writes to disk, you're writing 8K, 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 8K every microsecond, every millisecond that you're writing. And that's too much, right? So the operating system has the cache and waits for this cache to fill, and then flush that cache to disk, right? So that's a problem. We talked about the WAL, the write ahead log, right? If I told you to flush the WAL, change that WAL, I want to make sure the WAL is actually persistent. Don't put it in a cache. Don't try to be smart. Don't try to be efficient operating system. Go to disk. I want a way to bypass this cache that you have, right? So that's why most databases in certain operations, right, like the WAL, because WAL is critical, right? It says tiny things, but we need to flush them directly to disk. Okay? And that's called fsync. That obviously is called fsync. So if fsync is enabled, which is the default, I believe, then no. If fsync is disabled, right, which is off, that's the default, then it goes to the cache. If fsync is enabled, they force the sync, make the change, go directly to disk, bypass. Make it as a write through cache, right? Punch through a hole through the cache. So yeah, you can turn it off if you want, and you gotta get a little bit more speed, but in a danger of losing your data. I have that option off, by the way, in my testing data, because I don't care. It's a testing data, and I load the data on a daily basis. So if there is a crash, which is very highly unlikely, I just reload the game. And I didn't really notice much difference, to be honest. But never mind. So databases have this enabled most of the time. Not necessarily. Postgres doesn't have it enabled for like reading and writing pages, because we know that it's okay. Let's write it to the cache or operating system cache. Let's read it from the operating system cache, and that's fine. So if you think about it, Postgres has almost two caches. The cache is in the buffer pool. I think it's called the working memory, or maybe it's called the buffer pool. I forgot. And then there is the operating system cache itself. So two layers of caching. So yeah, so there's something to watch out for, right? So yeah, database engineering is very complex. So the final thing we're going to talk about is the undo log. Hussein, I wrote changes, right? And by the way, not all databases have this undo log thing. Postgres doesn't, because it does it differently. The undo log was designed specifically for give me the state of that row before it was changed. Might say, Hussein, what? Why are you doing this? Well, if you are in a running transaction, a long running transaction, you're changing, right? Right? You're making changes directly to the page, right? In memory. And you're writing the changes you made to the WAL. So now, what happened to transactions that started before you? Right? Transaction have this thing that's called isolation level. Since they started before you make this change and you still didn't commit, right? In almost all isolation levels except read and committed, those transactions need the old state of the row before you changed it. So it cannot read from the page that is dirty because it has the latest stuff. It does not need the latest stuff. It needs the old state. So what the database do is they keep a record of the undo log, specifically how this row looked like in its entirety, right? In a old row. In a specific log area that's called the undo log. Oracle, SQL Server, I believe. I'm not 100% sure about SQL Server, but MySQL and Oracle have this model, which is the undo log. Right? Postgres doesn't, because it uses versioning. It versions the row. Postgres makes the changes in the page, right? If you made an update, it's a new row in Postgres. So the old row already lives, which is perfect, right? I love this design, like much better if you think about it. Again, it's all personal at the end of the day. Preferences. But now, all transactions that want to read rows that have been changed, those rows don't exist on the page. So that they have to do a little bit more extra work. They have to go to the undo log, crack it open. I don't know what that means, crack it open. Just want to make sure that's slower. That's why I said that. And then take the page, the row from the page, and then undo the changes that, because the row is latest, you want to undo the changes. You want to apply changes to make it older, if you will, right? So you want to undo these changes so that it goes back effectively to the old state so you can read it. So a little bit more work for older transactions, or for that matter, newer transactions, right? Because the problem is we have a transaction that did not commit. We have a long-running transaction. That's why a long-running transaction is the worst for performance reasons. Because the undo log will keep filling up, and those transactions will have to go to the log and crack it open and apply the changes and roll back, if you will, to read the old rows. It has to do this all the time. And you might say you can do all sorts of caching, but this is work that the databases has to do, if you think about it, right? It's all work. Hussein, do you persist the undo log? I believe you should, right? Let's think this through. You should do the same with the undo log as you do with the redo log. Because the redo log tells you what's the final state, right? The undo log tells you the older states, right? And the correct way to do this is, in case of a crash, you're going to have a bunch of WAL, which is the reduce log, and then you're going to have the undo logs. And you're going to have a state of the page as it exists in disk. So in case of a crash, you have the undo log, you have the redo log, you have the old page. Okay? So what do? The correct order is take that page, and whatever is in the WAL is the truth. Apply all the WAL changes. Apply all of them. And then, because you might have applied stuff from a transaction that have been rolled back, right? Go and take the undo log and then undo the changes up until the point where the transaction had been rolled back, right? So you're going to redo, and then undo, until you reach a consistent state, right? That's one implementation that I can think of, right? Can you not persist the undo log and only apply the redo logs for transaction that has committed? I suppose you can, But then you have to differentiate committed transactions versus not committed transaction in the WAL, right? Which I believe that information doesn't exist. WAL has changes and it doesn't know if this is from this transaction versus that transaction. I suppose you can store this information in another data file containing the transactions that are being committed, but it's just easier this way. I don't know. Guys, this has been an episode of the Backend Engineering Show discussing the logs of the database. And pretty sure I missed some of this stuff, but I believe that's one of the most important things. Logs, undo log, WAL, and the redo logs. Gonna see you in the next one. Hope you enjoyed this one. Stay awesome. Goodbye.